Okay, thank you to be here, yeah, uh, for this second lecture on topic, let me say, observation, observability to introduce the Kalman filter. But of course, before introducing the Kalman filter, as I told you last time, I have to complete the concept of the observability, observer, and I would like to say today I hope to start with MATLAB Simulink, which I will implement and particular observer, not yet Kalman filter. The name of the observer is Lundberger observer. We will see also why this name. Let me share. It's here. Now I think you can see uh, the slides. This is the first slide of the lecture, which you can find in my study. Very quickly, do you remember ideas about some elements on the observability and about the observer? We can see in this scheme a system and a real system. Yeah, is indicated in an abstract form with this capitalized sigma. Yeah. You can see, I mean, I tried to explain last time that I measure a part of the state, about the state vector. I told you a little bit. I will come back during the semester many times. At this moment, I just flesh it out, no? What is in the state, but it's not bad what I told you. I mean, you remember just a few words about states or state vector. Do you remember last time we introduced also the language of matrices, vectors in the context of yeah, this topic here, observation, observability, and so on. Um, if I measure a part of the state, the idea, and a possible idea is to estimate, you remember, or observe. Estimate and observe, we have a difference. I will repeat it today during the lecture too. But let me go ahead with the short repetition. The idea is to um, estimate, as I told you, the rest of the states which I am not able, or which I cannot measure, or which I don't want to measure. The reason is sometimes it's too expensive, some kind of sensor, sometimes the variable which we want estimate is represent something extremely abstract, which belong just to the model. This will be more precise, during the semester with some examples. Yeah, the idea is to build this observer, which is in an algorithm, to estimate what I cannot or don't want, or as I told you, I have too expensive to be measured. Of course, I can do using also the input, but in general, we use the input because the input is available because it's the output of the observer. No? This means is our element with which I will try to control the system. Um, in this sense, the input helps, but we will see that strictly is not necessary to measure, but is it available can just help to identify. Identify means in the sense to estimate or to observe what I want to know, which I cannot measure. Nevertheless, as I don't know if you remember, I told you about very quickly about the Gaussian Markov theorem, which says under some conditions we will see together, the estimated variables is better than the measured variable. This means even though I have the possibility to measure everything, it makes sense, nevertheless, to estimate. Okay, here we see a little bit the goal, no? Because sometimes it depends on which kind of controller which I want to use. I need all states in order to control. But in this course, we don't speak about controllers. The Kalman filter on general and observers is used basically to monitor, to estimate. This means for different tasks. I don't need to introduce, or it's not necessary to have an excuse me, a controller to for implement an observer. Observer means just I can monitor. No? I can look what happens in some variables which cannot measure in this sense. Variable means also we will see together some parameters of the system, because the parameters is not constant. No? This is clear when we speak about the model. About the model, I told you. About the model, I told you, introducing this, excuse me for this first lecture, I introduced just an electrical system, but I am an electrical engineer. But we will see during the semester, but in particular for projects, we can apply these methods. I use the plural because we will see many variations of Kalman filter. Therefore, we say Kalman filters, plural. For the project, we did, I will sketch those, as I told you, some different systems with different nature, population dynamics. If you think about COVID, we did bacteriological populations. We did prey predators in the sense of fisher. We did a lot of application, not only motors. We did economical systems. Believe me, in fact, we will see also today that I will start with system which is totally abstract. X1, X2, it doesn't matter what X1, X2 represent. But just to start, it's a shame I have this material for the engineer. I introduce this scheme here, which is already the model, as in a graphical model. Please pay attention. The model, the concept of the model, if I want to summarize what I told you last time a little bit more in depth, the model is a representation. Is a representation of the reality. This means what we see now in the slide is a graphical model of what? Of the real system. Please let me close the email because otherwise sometime I have to answer. So, okay, this probably is important to look because, but I would like to close because otherwise I try to look the email. Okay, because as I told you at the beginning, I answered a couple of emails. And we need a representation of the system. A real system. Please pay attention. This graph is also real. I don't want to say that that is not real, but as a graph which represents a technical system which is built with coils, let me explain, so with permanent magnets and so on. What we need in our, let me say, structure, in our to realize an observer in this context is a mathematical model. It's a mathematical model which I don't want to say that this is not real. Of course, the mathematical model is real in the sense of the math. I mean, also a software is something a little bit strange, soft, but it's real in the sense of the informatics. Okay, this I don't have time to repeat. We build the model because also it's not important for you today to understand this electrical system because many students came from economics, from psychology. We are working, for instance, I will invite you in a seminar in the next weeks when I come back. We are working with the Kalman filter to identify, I told you, feelings, the mood. We modeled and we observe the oscillation of feeling of mood of a patient which is affected by bipolar disturbance, this psychological, I would like to say, disturbance. It's really interesting also in this sense. I will organize a seminar, believe me, and I think in November, but I need also to explain a little bit, Kalman Filter, of course, and to go ahead with the program in order that you can understand what we are doing. Probably December, because I don't know, it could be also earlier. I have to introduce at least some elements of extended Kalman filter, which is the impossible variation, one of the most important variation of the Kalman filter. Okay, about the model, do you remember what do we need independently? Which kind of model I have? I have to express the derivative of the states. State represent the energy or reflect. It's not wrong to say represent as a function of the state itself and input of the states themselves, because could be also more than one state. As in this case, we have a state which is the current, we have another state which is the velocity. Why that? Because we have the electromagnetic energy and we have the kinetic energy. At the end, I don't know if you remember, let me go a little bit ahead faster because I told you last time, but it's not the focus of the lecture. We can consider these three equations as the mathematical model of a system, which is the real system. Real means we have coils, let me say, yeah, it's strange because also these equations are real equations, but represent in a way to describe a reality which is more hard. Coils, uh, uh, let me say, uh, magnetic aspects, rotors, but it's not, believe me, far away from a model of a bank model. I will tell you about that. It's really quite similar, believe me. Do you remember I told you last time, the ability asset and so on. Very important, the form, inside the form, or let me say behind the form, we have something essential. The form is the derivative of all state variables, current, position, rotor velocity, equals or as a function of the state variables and the input. This formal aspect allows me to say that the idea is to monitor. The word monitor is clear. It's observe, it's estimate, to get information, Uh, is a function, excuse me, is to monitor the variation of energy because the current reflects the electromagnetic energy, the position reflects the work, the angular position of the rotor in this sense. The velocity of the rotor reflects the kinetic energy. I told you also last time the formula, 1 divided 2 L multiply current square, considering the energy, electromagnetic energy. I can do similar expression. I can tell you similar expression for the rest of energy. It's not at this moment extremely important. Look at this. Nevertheless, I have three initial conditions which represent, very important, the initial energy of the system because it's reflected, is the initial condition of current, angular position, angular velocity, which reflect, as I told you, the energy, initial energy. This plays today an important role, we will see. About the constant at this moment, it's not so important to go in depth in this constant of the motor. A few words about this structure here. We can see that I can transform, I can translate, remember the concept of the translation of this language here into this one. It's important because we will see today, or we will start today, to implement the an observer, which is not the Kalman, but something which allows me to introduce the Kalman and to implement in the software, not necessarily MATLAB Simulink, but in any kind of software, I would like to say general, the matrices play a crucial role. because as a structural language, row, columns, and the algebra of the matrix, matrix means also vector. Basically, in a vector, look the vector B. No? Do you remember last time we defined as the input map? Uh, is in a matrix is just one column. In this case, three row. The row correspond to the number of states, and the column specific for B in this case reflect the number of input. But this is a little bit more technical system theory, but it's intuitive. From here, do you remember last time I told you I don't have time to repeat how I can build this? For the matrix A, as the matrix, the name is transition matrix. In this sense, we will see n times n, in which n is the number of the states. Very important, you remember to notice this row, this column, excuse me, this column of 0, and then I come back this in order to repeat. Row multiply column, do you remember last time I insisted on this? I can show you that this language here is equivalent to this one. The advantage of this translation is that this language is a language extremely suitable for the computer because the computer works with matrices, believe me. And the matrix, in this sense, we can understand, reflect the structure of the system in all its aspects. The number of states, the organization of the states, and we will see with MATLAB Simulink a little bit better. This equation here, or that this expression here, reflects the output which I am measuring in this case because we are considering an observer. I measure the current. You remember our original hypothesis question. Measuring the current in output, or better to say, as a state, and the input in of the system. Is it possible to estimate, for instance, the velocity? Would like to add, as last time, it is possible to estimate also the position. Do you remember this? I can reduce the dimension of my matrix. This means the dimension of the observer because of the presence of this 0 here. This 0 means that I don't have feedback between position and the rest of the system. The rest of the system means in the electrical system and in the mechanical one. But this is specific for this kind of motor or this kind of structure. It could have an feedback. This feedback is important for the observability, if you remember last time, because if I don't have a feedback, measuring something is difficult to estimate something different. Again, to sum up, extremely important is the feedback between the states. In order to say, we will see today a little bit more mathematically, in order to say if a system is observable or not. It's important the observability, of course, because if the system is not observable, no chance. Now I introduce a little bit with feeling, no chance to build an observer. I mean, we can build an observer if and only if the system is observable. Now we will distinguish between fully observable, partially observable. But anyway, this is the basic concept. Without observability, now I give you just some idea. No possibility to build an observer. Then we will distinguish between different concepts of observability. Yeah, we reduce everything. Because now I will tell you again this new language, which is the language of the block diagram. Today we will go in depth on this. Why I reduced, remember last time that I told you very well, I hope, the dimension of the matrix and the sense reduce the observer. Because we can see here, I will come back how we can build this kind of observer for a system a little bit easier. But we can see from here, this language here, do you remember last time I tried to explain, reflect exactly this system here with 3 states, current, angular position, angular velocity, or if you want this. And it's just a translation, which we will see extremely useful in Simulink, which is an application of MATLAB, it's a graphical application. But from here is more clear why I try to reduce the order of the observer because I don't have feedback from phi to the rest of the system. Rest of the system means with the electrical part and with the mechanical part. In fact, we can see here, we have a zero here, which we can see that the phi is not represented in the electrical part. We can see also here, phi is not represented in the electrical part, but is also not represented in the mechanical part. This means if I don't have this feedback, I don't need the expression, or let me say the equation related to the variation of phi. I need, if I measure phi, but do you remember the problem is was so formulated. I measure the input and I measure the current. Yeah. It is possible to observe velocity, the velocity, yes, thanks to this feedback. I mean, if I have an instrument here, I can have an information about phi because the presence of this connection. Lens, low, last time I told you a little bit. But anyway, we have a connection. Lens in the sense in this system here, in the electrical system. About phi, no possibility measuring current to have information because we can see that the information go out, let me say, from the system without coming back. Here, this is the concept of the observability. Here, somehow, I will have information about the velocity. Think about a little bit abstract with this connection, this feedback. I think last time we conclude more or less here, which we can see again in more abstract form, what I already told you here. We have also x dot, x is the vector state in this reduced form, equals a multiply x, everything a is, x is a function of the time, of course, because the energy change over time. The idea is to observe how the energy change through the corresponding state, the variable. B, we can see here, this expression here and this expression here is exactly what I summarize here with some nomenclature. In general, we will see during the semester that we will be able to also manage a nonlinear system, which is sketched here at the beginning of this slide with the word in general, because the nonlinear system, at least in our course, nonlinear system, I will come back when we have a nonlinear system, the difference between linear and nonlinear, but I will now flesh out again the linearity is exactly can be expressed at least with a few words, even though we have let me say structure definition, but can be summarized with the concept that I can separate the contribution of the state with the contribution of the input when I want to observe the variation of the energy. The energy is again represented or reflected by x. The variation is x derivative. Do you remember in gymnasium? Derivative means variations. If I can separate, if I can distinguish in the model between the contribution of the state with the contribution of the input, we are speaking about a linear system. Last time I told you a linear representation of the bank. Okay, but I will come back on this. This must be for the variation of the state, but also for the output. The output which I measure, we can see that's also separated. In this course, we will consider always d equals 0. The system which I will consider in this course has d equals 0. But in the project, we can do also a different system. Why that? I don't know. It could be that I can introduce in a system with d equals 0, but it's not different in the sense. But I try to simplify. Let me say also the formal aspect. It's not only in the formal aspect. It's not difficult, but I would like to leave this aspect here probably for a model, for a project. It's a model problem. I mean, of course, depends what I'm measuring. Please pay attention. Depends what I'm measuring. I can sketch probably in a possible project in which I want to consider something to measure which depends on U input. In this case, D is not zero. It could be that I will tell you, but for a project it's possible. It could be something a little bit challenging, because the project, as I told you, I will give you the MATLAB Simulink file, basically the MATLAB Simulink files which we are considering during the semester, and then modifying this. This is the sense. We can generate or we can answer, we can solve the problem which we define together for the examination. Okay, now, here is the new thing. Or at least I would like to insist. I started, I think, very, very shortly last time. Look at this concept here. Now we will go more in depth on the observability using this abstract example. The abstract is more important now to understand very well because, as I told you, we can consider any kind of systems, economical, biological. In fact, I gave directly the equations. X1 could be the liability, X1 could be the population of fishes, everything. Look at this first equation. X1 derivative equals minus X1 plus X2. Then we have the second equation of this system, which consists of two states, X1 and X2. X2 derivative equals minus X2 plus U input. Question. Please build the block diagram of the system here. The block diagram is not only theoretically important to understand a little bit better or to figure out the observability, as I told you until now, is important because we will use the Simulink in MATLAB in order to simulate, in order to validate our observer. The observer itself can be built in Simulink. Typically, the Lundberg observer we build directly in Simulink. Kalman can be done also in Simulink, but it's extremely complicated. We use in a MATLAB file. Look, why for the engineer is easy, but why this representation is equivalent to the representation using equations. Why that? Because X1, which is our goal together with X2, but let me concentrate on X1, the state X1, came from the definition of the integral, from the definition of the derivative, from the integral of X1 derivative, assuming that I know the initial condition of X1. Probably you remember math, no? The integral of X1 derivative, if I know the initial condition of X1, equals X1. I don't know, also in gymnasium, you know that. But anyway, the integral of the derivative, so roughly speaking, is of a variable, of course, is the variable itself. But we have to know the initial condition. Here is not indicated the initial condition because this scheme reflects in this form exactly what we do in Simulink, in which the initial condition is inside the block. We have to click on the block. I will clarify, I hope today or not later than next time, when I will show you an implementation of a Lundberg observer. Now, X1 derivative in accordance of this equation here equals minus X1 plus X2. I mean, this arrow means that this variable is going in input to this block here, which realizes the integral of X1 derivative. The equation says that X1 derivative equal X2 minus X1. It's written here. This means if I have the possibility to represent this subtraction X2 minus X1 with a block, I will put this block here, the output of this block X1 derivative, and the input is X2 minus X1, in which X1 came as a feedback from the output which I already defined. And this loop represents exactly, with another language, the dynamics of the physicist of the x1, which is represented in the same way with this equation. Please keep in mind, each equation is at least is representable, at least with a one loop. We went through one loop. Basically, we have also x2, which came from another loop. Therefore, I told you at least with one loop. No? I mean, if I don't have here x2, the equation x1 derivative equals minus x1 is represented with one loop. A dynamical system, we need a dynamical model. A dynamical model, if you want, because the equations is the model. The word system is a little bit ambiguous because can with the word system I can represent, I can indicate many things. Equation system. But I don't know, probably we can understand when with the word system I intend a real system. Probably it's better if I say the real system, the equation system. Okay, I can do the same for the second equation, in which we have an input here. Please pay attention, I made a mistake here in the representation. Yes, U, I, and P is the same. The problem is it's not in a picture. I have to redo everything to correct, but I am telling you, this is the same U which we have here, even though it's not indicated I and P, which means input. It's the same. It's easy to see, no? Because until here is exactly the same as I told you before. Then we have a minus x2 plus u input, which can be realized, at least with this new language, with these blocks, or with the block plus minus. Look now, very important here. If we measure x2, assuming that I can measure that x2, in our output representation, we have the matrix C is 0, 1, because X is not written, but is intuitive, is as before, is the vector of the state. First component X2, first component X1, second component X2. C0, 1, I will take, let me say, take X2 as a possible measured variable. We can see here, X2 equals C multiply X. X, I didn't write here, because I don't have much space, is x1, x2 as a vector. This means 0, 1 row, which multiply the column x1, x2. X2 is the result, which is the measure which is the variable which I want to measure. But measuring x2 is easy as before to realize from this scheme that the system is not observable. It's not observable because I don't have idea about the variation of x1, because x1 does not contribute to the dynamic of x2. The reason is here. x1 is not represented in the dynamics of x2. The system is not observable if I measure x2. But if I measure x1, is the next slide, everything is as before. I change just what I am measuring. We can see here. Now, the map of the sensor is not 0, 1 anymore, but E1, 0. X1 is C multiply X. I measure X1. But if I have an instrument here, now I can say that the system is observable. Of course, because measuring X1, I have a nevertheless information what happens on X2 thanks to this feedback. We can see from the equation, excuse me, measuring X1, this means having information about the dynamics of X1. X2 is representative. This is a very intuitive idea of the concept of the observation, but reflects, the basic concept. Of course, I can improve also the concept, but let me remain on this level here. Look, this now we have a small variation in the system. In fact, we can see that I added here with plus or the minus, it doesn't matter. I can also write plus x1. The system is exactly the same as before, but I added here a contribution of x1. It doesn't matter of plus or minus x1. This means now I have this feedback here. Oh, this connection isn't a feedback, but it's a connection. Now, it doesn't matter what I measure. It doesn't matter what I measure. In this case, we say that the system is fully observable because it doesn't matter what you measure. We have the contribution of two variables in both equations, if you want, of the channels. Now, I think we have a good idea about and a good intuitive idea of the observability. I distinguish between fully observable and not fully observable, but it's intuitive too. No? If I don't need to distinguish what I measure is fully observable, this means I can measure whatever I want. Here we have a possible definition of the possible, because we have many definitions of the observability. The definition is referred to the fully observable. But of course, it's clear what I intend for fully or not fully. I don't want to insist on this because just to show you uh, how possible to say that we have a formal definition, but it's not a definition self-sufficient, I would like to say, because I have to define the concept of distinguishability. This means that I can distinguish, I can notice the difference between the states, but just to show you that we have definitions, and the definition is related to also other concepts, finite time. Don't learn the definition, just to give more feeling. But again, I would like to emphasize only through the system output. As I told you at the beginning, the input can help. We building uh, an observer. We use always. We already used in the scheme the input because it's available. But for the definition, it's not necessary. We can see also from this possible definition. When I speak about why I speak about possible definition? Because we have many definitions. I don't want to go in depth on this. Here is something which is nevertheless unclear for us because I didn't define the distinguishability concept. Finite time is a little bit how we can understand. It means I don't want to wait infinite time at the end of the universe to distinguish two variables or the three variables or the state variables. Intuitively we can understand, but of course it's not complete in the sense. But I would like to show you that exist possible definitions, different, it's a shame, in accordance with the definition, which I did input the distinguishability, finite time we can understand. Very important, nevertheless, to emphasize only through the system out, because the input helps. One input helps. If you have two inputs, also helps more. But it's not, let me say, necessary in the context of the observability. Don't learn this just to have a feeling today. Now, this is extremely important. Nevertheless, I try to slow down a little bit now the lecture because we have here some formal aspect, and behind or inside the formal aspect, we have something essential. Here, I would like to show you a test for the observability. And the test came from a theorem we can see here in the red part. This is a necessary and sufficient condition for the observability of a linear time invariant system. Therefore, I would like to discuss some aspects. I don't have time to demonstrate the theorem. In this course, I cannot demonstrate the theorem for different reasons. Basically, for the time, but not only. In complementary study, you are not engineer, or at least some of them, and this means it will be really boring. I mean, it's not effective. For engineer, of course, in the project, we can also consider some, excuse me one second, also some theoretical part, we can also work theoretically, but the goal of the topic of the course in this topic is to be able at the end, each student should be able to realize, I would like to say, a Kalman filter autonomously, using also my software, MATLAB, Simulink, which will be my study, but I would like to consider more the realization of the Kalman filter than the theoretical aspects. Again, here isn't a theorem, isn't an if and only if theorem, necessary sufficient condition. Please pay attention for a linear time invariant system. At this moment, until now, I didn't tell you about linear time invariant. I told you just roughly linear system, linear system. In this sense, I included time variant, excuse me, time invariant and time variant. It makes sense to speak about now about these differences because the differences play an important role in the Kalman filter. We will see uh, when we speak about augmented Kalman filter, extended, we will see that's extremely important to understand and to work with these concepts. Again, we are in the present now. Probably I told you. I don't remember. Is we are in the present now, until now, in the presence of linear time invariant system, because the parameters of the model does not change over time. Let me show you concretely what I intend. Here is a little bit too easy because the parameters is 1, which multiply x1, or -1 if you like. 1 will multiply x2, which is constant. 1 is constant. It's too trivial. Let me show you what I intend here. Yeah, yeah. R, L, K, M, J does not change over time. If they change, we are speaking about linear, because about the linearity I already told you, time variant system. If the parameters which characterize physically the system, physically, let me say so, cannot change in the model. Really, they change. Not all, but anyway, in this case, for instance, it's easy to see that the resistance changes because change the temperature. Or if you like, change because the resistance changes because change the material characteristics. This means if I model the system with R constant, I have to consider that the model does not reflect exactly the reality. Isn't a problem? In a normal observer, could be a problem. In the Kalman filter, is not a big problem because it's a more advanced observer. I will come back on this. But now the goal of this slide is to explain also, not only this, the difference between time variant and time invariant. I think this is enough what I told you. I mean, the matrix C, the matrix A, if they are constant, we are speaking about time invariant system. If the matrix C and the matrix A change over time because the parameters which characterize the system change over time, basically change over time, not all, but in the physical system, I would like to say all, but in the bank, for instance, yeah, could also change because the interest can change. But anyway, if you sign a contract in investment in which the interest is fixed, this is that not change this parameter which characterize the system, interest system. But it could be that you sign a contract in which we say the interest depends, I don't know what, for the boards, it depends of the gold price. I don't know. In the sense, change also in the parameter of your system, the bank system or contract system. Okay, let me go in depth on this. I don't want to demonstrate the theorem, should be better to understand, But intuitively, it's quite clear that the test of this observability depends on the matrix C and A. Now, the structure of this matrix Q is in a matrix. To explain this, I needed to show the theorem. I don't want to do, but it's clear that depends on C. Why that? Because do you remember, with this choice of C, the system is not observable. With this choice of C, the system is observable. The system in the sense, how about, but I would like I don't want to add some consideration. It's clear what I intend. If the system is this now, do you remember the concept of fully observable? The system is again fully observable. This means it's also clear that the test depends on C already explained, but depends also on A, because the matrix A of this system here is different with the matrix A of this one. Because here I added in a feedback. The matrix A here is, look, minus 1, 1, minus 1, minus 1, which is not exactly this, because it's minus 1, 1. The first row is the same, but the second row is different, because the second row is 0, minus 1. It is not minus 1, minus 1. This means just flesh out. It's quite clear that depends on C and A in case of linear time variant system. Now, A squared and so on is a little bit more difficult to clarify, but if you look just a practical consideration that we stopped to build the matrix Q considering A up to n minus 1 means basically that depends on the number of state, because n is the number of states. This means it seems to be that the structure here reflects the concept that, of course, depends on what I am measuring, depends on the structure of the system, and also depends, let me say, reflect that I have to have a connection everywhere. I have to have a connection everywhere in order to obtain the observability. Of course, it's an explanation more intuitive, but I don't want to demonstrate the theorem. We say if the rank, I don't know if you remember math, of Q equal n, full rank, in this sense, the system is observable. Full rank means basically that I have a connection using this C is not related to the full observability, because depends of C. At least we can interpret it this far. I will come back on this with MATLAB Simulink probably next week, because I have just 25 minutes. I would like to go ahead, but I will clarify better with the MATLAB Simulink again. Here, just to flesh out that if the system is now variant, or the time variant, linear, still linear, but time variant, we can see here time variant, because the matrix A, B, and C can depend of T. We can see that the test is a little bit more complex, but the condition is nevertheless in if and only if. If and only if means necessary sufficient condition. The reason is that the system is still linear. Don't learn this, but just to show you that we have another test, relatively similar. What we preserve, thanks to the linearity, the necessary and sufficient condition. But of course, the test is a little bit more complex. Now, we are going inside the observer. Today, we will see now in detail the observer. We have here two pictures at the end, left and right. At this moment, I would like to concentrate on the left, because about the right, I have to introduce the concept of the discrete observer. I have to, in general, introduce the concept of a discrete model. Why I put nevertheless? I put nevertheless that in order to introduce that basically we will need a discrete representation because the Kalman filter is realized in discrete form. At this moment, we can see nevertheless that quite similar in order to show you that once we understood the continuous observer, is not a big problem to understand the discrete one, even though uh, discrete modeling, discrete control, discrete observer in sense of in theoretical aspect is really heavy, no? But for the implementation, not a big problem. Uh, this semester, I have a course. I have a course in master. If you are interested, you have also time to enroll you on discrete control and optimization. I don't have time to also in this course to tell about the discrete observer, but I do here with the Kalman filter. Anyway, if you are interested, look, Mercorelli, the course is discrete, something like that, but you can recognize with the word discrete under my name. If you want to go in depth on this part, more control than identification, but I will tell you about also identification in the other course, but no Kalman filter. Kalman filter is here. Let me concentrate on the continuous observer. We can see this this picture. This picture. Mm, with the yellow block or the inside the yellow block, we can see the representation A comma B. The output of this block is a little bit, let me say, is in a sketch. X of t, which is in input of the block C, the output of block C is Y. With this representation, I would like to indicate that the system, the real system, yellow structure, is representable exactly with the matrix A, B, and C. Of course, it's an artificially concept. Yeah? It's an artificially concept because practically it's never possible to represent the real system with the matrix A, B, and C. But if it is possible, we have here the possibility um, to observe, please pay attention, in open loop, what happens in the system if I replicate in my software. Here is the software is a little bit far away, but in order to understand what I want to say, uh, the matrix A and B, in order to observe what happens in X. I mean, believe me, if I am able to say, if artificially the system is totally representable with the matrix A and B, C is what I have an output, but very important is the state, to observe the state. I can replicate, I can build a copy of the matrix A and B in my computer, and I will have that X hat equals X of t. Please pay attention now, assuming that the initial conditions of X vector as a vector equals the initial condition of X hat. If you remember a little bit in math, we can understand that two differential equations, which basically have the same parameters, have the same, let me say, solution if the initial conditions are the same. Otherwise, no. But with this scheme, with this open loop observer, it's not possible to correct an error, even though A and B are the same, if the error appears in the initial condition. As I told you now, we know from math. We have, if you want, I can show what I intend with the lateral camera. Let me take a better slide. What I explained now until now can be summarized in this form. X of t derivative minus X of t. x0 times 0 equal 1 means, you remember, if this is 1, this is x of t. Easy from gymnasium, from first lecture in math. No? But now, if I have something like that, let me say 0,5. This is a different, no? A different. I will have two different, let me say, solutions. The solution means, in our case, the profile of my state. Question is, can I use this open observer? No, I cannot use. Even though I have A and B exactly, assuming the A and B represent exactly the real system, I cannot use. In fact, Professor Lundberger, now we understand the name of Lundberger observer, realizes one of the first observer structure, the name Lundberger observer, considering a feedback between what? Between what I am measuring and what I am observing. For instance, if I observe the variable x1, if I measure the variable x1, I can observe the variable x1 and I can correct with the difference in between using the matrix L, the initial condition that which can be different. I mean, here the hypothesis is I can represent perfectly the system, use the matrix A and B and C. Even I have an error in the initial condition, I can, thanks this scheme, correct this error. But this is possible because of the feedback. Now, for the control guy, for the students who attended classes in control by me, is quite clear. The effect of the feedback can correct errors. But for the rest of the students, believe me at this moment. But this is intuitive. The same consideration can be done for discrete. Forget at this moment discrete. But we can see that the structure is quite similar. The theory is not the same. We have to consider many things. But let me say the practical application, even though the practical application is based on the theory, we cannot separate. But in this course, I cannot insist on we will see in Kalman filter, which is in discrete form. I can realize the discrete form also from Lundberg. It could be, I think I will introduce a little bit. But practically once clarified some concept, the structure we can see exactly the same. I introduced this discrete system here in order to let me say, to start to say that our goal is the discrete form of the observer, but we can see formally is the same, theoretically is different. To sum up, what we are doing, we want to realize the software. The software structure is inside is dashed, which consists of a mathematical model. But mathematical model, I told you a lot. The different, what I am measuring. C here represent a little bit abstract here. What I am measuring, could be also this picture could be also improved. Um, because yeah, but it's not bad. It's not bad. It's a little bit difficult to clarify with the picture what I want to do, but we will see in MATLAB Simulink quite clear. In general, yeah, assuming that here I have what I am measuring. But it's not wrong. I compare the corresponding variable which I am observing, and with the error between what I am measuring, what I am observing, thanks to the matrix L, could be a matrix, could be a vector is also a matrix, I can correct my initial error in term, the error in term of initial condition in this sense. We will see that the observer which I present now, I will correct this um, error, but asymptotically, because I will present an asymptotically observer. Also, in the version of the Kalman filter which I am implementing this course is an asymptotically observer. Okay, I think is enough what I am telling you now. I need a few minutes to introduce some calculations in order to understand better what I am doing. Look, here we have the system. We can see here this sigmoid system represented in this form. In the lower part of the slide, we have the continuous closed loop observer, which, if I don't consider this part here, if I don't consider Cristi, ciao. If I don't consider this part here, if L equals 0, is exactly the same, but we have a different initial condition. This is the idea of this last part of the lecture. To understand better what is this uh, mm, asymptotical observer. I mean, it's clear that if x hat 0 is not equal x 0, and L is equal 0, we have here also, instead of x hat here, because as I showed you with the lateral camera, we have two different x and x hat. Because, let me say, the dynamics, uh, totally not, but it's different. No? Now, the idea is to introduce another input. We can see from here, no? We have another input. We have your input in both, and we have another input. We try to correct. It's a shame in this scheme today, in infinite time, the error which we have. Infinite time means asymptotically. Let me do some calculations. At the beginning, I repeated the observer structure. Then I have what I am measuring, y, what I am observing in correspondence of the measured variable. C, A, B, C are exactly the same. I assume that I know perfectly the system, of course, and I can represent perfectly the system. This, of course, is something extremely abstract. If I plug in y c multiply x and y hat c multiply x hat in the first equation, I have this equation in the middle. If I consider now the real system, which again, I assume that I know perfectly the real system, and I subtract the equation of the observer from the equation of the system, we obtain this one. It's easy to see. If I do this equation minus this equation, I will have this. It's clear. Then, if I put in evidence A here, we have A parenthesis x multiply x hat, x hat parenthesis. If I put here in evidence C, we have L C parenthesis, we multiply x minus x hat. If I define x minus x hat as the error, estimation error, because the idea is to have x hat equal x, is here, it's clear. The error is x minus x hat. It's easy to see from here, because here we have E error derivative, equals, if you remember what I told you with what I put in evidence, equal this one here, because here we have a nevertheless L multiply C multiply the error, and here we have A multiply the error. This means I can write everything in this form. I skipped some calculations, but I told you about the calculation with an initial error, which is x0 minus x hat 0, or at time 0 in this sense. But if you remember a little bit math, when the error is going to 0, the error is going to 0 means x hat will approach to x in infinite time. If you remember, also I repeated also today with the lateral camera, if the eigenvalues of this matrix A multiply LC have real part negative. I don't know if you remember math. If you don't remember or if you don't know, believe me. But that's I can do. I can realize because I have L, which I can design. L does not belong to the system. L is something which I put artificially. I was clever to say I can consider the matrix L, which is nothing to do with the system. This means I am free to choose L. We will see next week a little bit the how I can build the matrix L, or I can do now probably. So we fix also this concept here. About this side, at this moment, I don't want to, as a little bit more for engineer. I will come back probably next week when we implement everything in MATLAB. Let me conclude this lecture, this 10 minutes more or less. I would like at this moment skip this. I will come back next week because we can see MATLAB. No? We can see MATLAB. This means it may make more sense to speak about this next week. It could be that I reformulate for you the lecture in the sense I will move this theorem here later. Yeah, let me show you these 10 minutes, these boring calculations, but you don't have to do the calculation because next week we will see with MATLAB we can do everything. But I think it makes sense now to skip these 3 slides. We will come back next week with MATLAB. As I told you, we need MATLAB probably to understand better and to avoid these calculations too, because MATLAB does everything in 1 microsecond. Very important to understand what MATLAB does. Let me tell you about this slide here, and also the next one. It seems to be complex, but it could be better to proceed with this L matrix because we concluded this part of the Bob server with this L matrix. Again, as I told you, we have an asymptotical observer. This means I will have x hat equal x, both a function of t, in infinite time. Is this a problem? Not really. Practically, not really, because we can speed up uh, this dynamics as the dynamic of the observer as we want. Practically, we use this. Of course, if we want an observer in finite time, I don't have time to tell you in this course. We have to introduce a different feedback. But let me remain on this. About finite time, infinite time, we will continue next week. Let me do this calculation in these 5 minutes. As I told you, you have to place the eigenvalues of the matrix A minus LC, thanks to L, which is free. C is a little bit also free because I can theoretically choose different observer. This means different C matrix. Sometimes it's not so totally free in the sense. For instance, if it's not observable, we cannot choose. We have already seen whatever I want. But let me come back on this. I can place the eigenvalue of A minus LC as I want, assuming that the system is observable. About this theorem, I didn't tell you, uh, but yeah, let me see. Probably it could be nice without go in depth. look at this sentence here. If the pair means the matrix A and C, which characterize the observer, do you remember we have seen the observability is characterized just C and A, is observable in a way to express, in a way to express the system in terms of observability just using the matrix A and C. The reason is that in the test which we have seen today, the linear invariant system is characterized by A and C. Is observable, then the eigenvalues A minus LC can be placed arbitrarily. Of course, we have also the theorem goes also in the other direction. Goes also in the other direction. Basically, if I can place arbitrarily the matrix, the eigenvalue of the matrix A, L, the matrix A minus LC arbitrarily, the system of the pair AC is observable. Here, we consider just the theorem in one direction. Now, let me show you the calculation of L. I don't know if you remember math. How can calculate the eigenvalues of a matrix? Do you remember if the matrix is M, the matrix M is a matrix, I have to calculate the determinant of lambda minus M equals 0. This is the theorem. Now, the matrix M in our case is A minus LC, but L is unknown. But now the problem is inverse. The problem is fixing lambda 1, lambda 2 in our case, calculate the matrix L, or the vector L in this case, because we have just one input, characterized by L11, L21, which realizes exactly these two eigenvalues, given the matrix A and the matrix C. Look, this example here is exactly the example which I presented today in the morning when we started, after the repetition, which consists, you remember, x1 derivative equals minus x1 plus x2, first equation. Second equation was x2 derivative equal minus x2 plus u input. U is not relevant. Do you remember I told you the matrix B is not relevant in this analysis. Therefore, the U is not relevant. Now, if this is the matrix A, this expression here means in terms of matrix, lambda in the matrix form. In math, we say multiply by the identity matrix. Therefore, we can see lambda in form identity matrix minus parenthesis A minus LC, in which L is parameterized by L11, L21. If I do the calculations is not so difficult, because we have to multiply this column, multiply this row, and we have this one. Then I have to subtract this element with this one. We can see here, minus 1 minus L11, 1 minus 0. 0 minus L21 is minus L21, minus 1 minus 0 is minus 1. Then I will subtract as intuitive. To understand this calculation for the engineer is easy, because we have seen in many courses. This matrix minus this matrix, this one, in accordance with the rules, I have to subtract, in this sense, but sum algebraically the corresponding elements. And we have this. The determinant, probably you remember, is this here. And we can see that at the end I have the equation 2 and 3, which equation in the unknown L11, L21. Why that? Because lambda 1 and lambda 2 unknown, because I fixed in accordance with the speed which I need to realize the observer. Even though the observer is in infinite time, we can nevertheless define the velocity of observation. We will see next week with MATLAB. In any case, we have here two equations and two variables, L11, L21 to be calculated. With MATLAB, we will see that we don't need to do this by foot, let me say, or by hands, but we calculate with a particular command. Assuming that the system is observable. We will see next week that if C01, you remember this at the beginning today, the system is not observable. We have some problems. I will clarify which kind of problem we have. Very important now uh, to understand, we will see a little bit the calculation next time, that depends of course of C. Because at the end, if C does not guarantee the observability, we will see next week in detail, look, we cannot fixed arbitrarily lambda 1 and lambda 2. We can see that we have just L21, which can be calculated. We can see from here. Because collapse, I will tell you in detail next week. Because we have two equations, but the two equations are the same. It is possible to realize an observer. It is possible, but with some limitations. I mean, we cannot place arbitrarily the eigenvalues. Let me, yeah, I don't want to go in depth here because we need a little bit more time, but as an introduction of next week. Next week, we will conclude with the implementation also with the Lundberger observer. I will a little bit clarify a little bit better this theorem, a little bit this proof very quickly, and very important, we will try to implement, therefore we have this MATLAB here. And we can understand, in any case, I hope better what I told you with these calculations, and then I will sketch out this. We introduce with MATLAB Simulink the concept of the Kalman filter. Probably before introducing the Kalman filter, I sketch just a few concepts about the discrete system. Even though, as I told you, we don't go in depth on the theory, but we need a little bit for the students who don't know anything about discrete systems, what is the difference? This I can do. Okay. If you have questions, I'm here to answer your question. Please question me. Now I am here for you. Otherwise, at this moment, I don't have to upload any material, but next week I will upload the software, MATLAB Simulink. I will upload, I don't know if I have some slides, some manuscript, let me say, to be uploaded. This here is not, it is just something, the consideration of this we don't need. If you have questions, yeah, Nurmatov, question me.
Professor Mercorelli,
Yeah.
where I can find this video recording of our course?
Yeah, I didn't realize yet, but I think at the beginning of November, when I am in Lüneburg, I will do it. The idea is some colleagues of Loifana proposed me to realize an YouTube channel. At this moment, it's not so extremely. I mean, we are in in the initial phase, but I think I will do it. And if you want, if you need immediately, I can send you per my share, which is in a repository in Loifana. Otherwise, if you have a patience in a few weeks, my idea is to realize also roughly a YouTube channel with all my lecture. Some colleagues of mine, they have also in other universities more, let me say, popular than by in Loifana, but this is allowed. If you need immediately these two lectures, I can send me an email. I can send you per my share, which is in Loifana, let me say, repository. As you want, I can do that for you in my share. Otherwise, if you can wait 2, 3 weeks in November, we realize, because I am convinced that can help. But believe me, come to the lectures, in particular, if you have the possibility to come to in the present when we will start also in a hybrid form. Hybrid form will be always, yeah? This means I will record it in any case, but the lecture is more effective in the presence. Anyway, let me know if you need. I can send you per my share. Otherwise, if you want to wait in a couple of weeks, I will realize in channel with all my lecture, not only for this course, in which you can recognize with the name, which is this your lecture in the sense. Let me know if you want immediately. I can do per my share. It's a little bit more complicated. I have to upload in this repository. It's free for all students, and then you download. Let me know with an email, because I need your email, um, because in the email I will write the address of my share. I mean, it's an email. In the email, it is in a link in which you can download.
Okay, thanks for the response. I
As
can.
you want, I can do it for my share. Otherwise, in a few weeks, I will realize. Other questions, technical questions, but we are on the beginning. We will see that we increase a little bit this math aspect slowly, and then we will relax uh, with implementation. Implementation, typically the students like the implementation, because uh, it's not so difficult to be understood. And then I will upload working file, but you can, once we have the access to MATLAB, this means in remote, or if you have in your computer already, we can really test how it's working with the working file, which I will present, we will explain during the semester. I have already prepared files or the software, because otherwise I don't have time to build online, because sometimes it's really a lot of lines, a lot of variations, but I will explain each line. Okay, questions? If no, next week again, just in online. No hybrid, not yet. Hybrid means that I am in Lunenburg. This moment I am out, and I have the permission to do that, even though in complementaire very often the professor realize just online. But when I will be in Lunenburg, you can meet me in the room also, and also again per Zoom in hybrid form. No? Okay, thank you for your attention and your interest.
Paulo, hi.
Yeah,
Can we have a few minutes after the
yeah.
course?
I conclude. I stop now the